connecting a function with its first derivative and second derivative. Okay. What does the first derivative tell us? The slope. What does the second derivative tell us? Concavity. So, here's the function. Here's the first derivative. What does crossing the line at C tell us? What is the appropriate calculus-based justification for the fact that f has a relative minimum at x equals c? What is the appropriate calculus-based justification for the fact that the relative minimum of this function is right here? Well, what happens right here? What does the slope do? Slope goes from below to above, which means it goes from a negative slope to a positive slope. So when it crosses the x-axis, it goes from a negative slope to a positive slope, which is the justification for why that should have a minimum at that point. Okay? Get it? You're getting what I'm trying to lay down here. Okay? Here's a function. Here's its first derivative. So, why can we say that the function is always decreasing besides, well, we could see it? Why else can we say that? The first derivative is always below the x-axis, so it's always negative. Okay? Getting that? Okay, so that's first derivative in function. That's easy peasy lemon squeezy. Let's look at second derivative in function. Okay? What is the appropriate calculus-based justification for the fact that g is decreasing? Or, well, no, boom, this one right here. Given that the first derivative at c equals 0, what's appropriate justification that we have a relative minimum here? Okay? What about the second derivative tells us that our minimum is here? Knowing that the first derivative at c is 0. Well, because this is positive, it's concave up. And when it's concave up and the first derivative is 0, remember though the super easy assignment where the first derivative is 0 and the second derivative is positive, it's concave up, which means there's a relative minimum there. Okay? There's a relative minimum where it's concave up because it'll be concave up if the second derivative is positive. Okay? So it's concave up, so that has to be a relative minimum if the first derivative is equal to 0. Okay? Why is this concave up? Because the second derivative is positive. If the second derivative is positive, it's going to be concave up. Okay. Why is this a point of inflection? Because the second derivative crosses the x-axis at that point. Okay? Second derivative crosses the x-axis at that point means it's a point of inflection. Okay? Those are all important things that you'll have in the first two assignments. Then your third assignment will look like this, and this is where people were hating life and wanting to jump off the top of the building last year. So, because I didn't teach it that well last year. Now I'll do a better job with this than you guys. One of these is the original function. One of these is the first derivative. One of these is the second derivative. Okay? Which is which? That's fine.
The first one is the first second. Original. No, first one, second.
The first one's first.
The second
No,
one.
first one, second one.
It's 2, 3, 1. I don't know.
3, 1, 2.
Sure.
Scroll down.
3, 2, 1.
3, 2,
One is the
2,
last
1,
one.
3.
Nate Ricky, what do you think? 3, 2, 1. You are correct. Now let's see why. Okay. If this you got to just guess in your mind what the original function is first. Now, what I usually do for guessing is I take the most complicated one and say, well, that's the original. Okay? So what?
That's exactly what I did.
Okay, so what's happening in between a negative and basically 2? The slope is? No, the slope is
Negative.
decreasing. It's a negative slope here. And it's also a negative slope. Actually, it's a negative slope all the way to 4, right? So it's a negative slope all the way to 4. So the first derivative should be negative all the way to 4. Is there a function that's negative all the way to 4? 2. So this would be the first derivative of this. So this is a function. This is its first derivative. Now, this thing is concavity. Does this change concavity? Well, you see it's kind of pouring down here, and then it's being poured into here. So this is the cup, and this is concave down. So it looks like it maybe changes concavity somewhere in here. Ooh. Concave down, because the second derivative, concave up. Now, if you said, well, this is the original function. If this was the original function, slope would be negative to here and positive after that. Hey, this would be the first derivative of this. But remember, the first derivative of the first derivative is the second derivative. Okay? So, this cannot lead to this because this has a positive slope the whole time. If this was a derivative of this, it would have to be positive the whole time, and neither one of these are positive the whole time. So this has to be a derivative of one or the other, so it goes 3, 2, 1. Okay? So don't jump off a building when you see these. Okay, this one.
1, 3, 2.
1, 3, 2. Jeff.
Oh, that's not true.
Trey is going with. All right. So 1, 3, 2. Okay. So positive slope up until this is -1, -2, -3, -4, -5, -6. So positive slope before -6, a negative slope right at about -2. So -6 to -2, the slope is negative. So are we negative somewhere in between -6 and -2 anywhere? 3 is. So would 3 be a derivative of 1? Sure. Okay. And then we'd be positive the rest of the way. It's positive the rest of the way. We have positive slope before 6, positive before 6. So definitely 3 is the derivative of 1. Now, is 2 the derivative of 3? Okay. Negative slope all the way to here, negative to there, positive the rest of the way, positive the rest of the way. So if we do what Trey said, 1, 3, 2, this would be the second derivative. So concave down until about -4.5, then concave up. Concave down till -4.5, then concave up. Yep. 1, 3, 2 would be the order. Now let's look at, I thought I had one more that was really, 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 really difficult. Well, I guess I don't. So, shoot. So, there you go. Get to work on these. They're fun ones.